the exact same structure, it just hasn't been unfolded yet. But yes, that is ozonolysis in a very, very nice and compact nutshell. All you're doing is splitting apart alkenes to create carbonyls. That's your goal there. And like I said, the big dead giveaway is that you're adding ozone, and then like I said, some sulfur derivative to then split apart those carbonyls.
So on the exam, we only have to draw one of them, or do we put like times two?
Yes. So for the exam, you would only have to draw one of these equivalents because again, once you split this, you end up with two linear structures that are identical. And as you mentioned, you can also put a times 2 there if you want to make it more accurate. But either answer would be valid. You can draw one structure times 2 or just draw the one structure by itself.
Can we number the carbon ring to the right? What if we number it to the right? You see how we go like 1 and to the left? Can we count it to the right?
So what if we numbered it the other direction?
Yeah.
So if we numbered it the other direction, so if we said this was 1 all the way to 7, then we would just have the carbon-oxygen double bond at the 1, 2, 3, so it would be at 1, 2, 3, just be on this side of the structure. So again, it all depends on how you number it. It'll be near one of the two ends. I only put the hydrogens here. It's a good question. So why do I put the hydrogens there? I just put them there just for the sake of symmetry. In reality, you could leave your answer just like this, and it's perfectly valid. But that poor aldehyde looks kind of, I don't know, it looks naked without that hydrogen kind of sitting there. So we tend to just draw it on there. And for the sake of the graders, if they don't see you draw that proton there, they may very well mark you wrong for that. We've seen that on midterm 2, we've seen it on midterm 1, so when in doubt, try to make it all symmetrical and try to put that proton there. But again, that answer would be valid even without the protons there. So it's just a matter of saving you a regrade form, I guess, and some time. But good questions all around. Any other questions on ozonolysis? No, you will not need to know the arrow pushing for this. And even if you did have to know this, it would hurt me to show you because that's just mean. It's a mean reaction and mean to draw. So just know that if you got ozonolysis going down, you're turning an alkene into a pair of carbonyls. Any other questions on this guy? Any questions on the nightmare that is? Not too bad, right? Not too bad, not too bad. All right, let's look at the next guy. Ooh, what do you know? We got an alkene, we have diatomic bromine, but now he's got a friend accompanying him. This is going to change our reaction significantly from what we saw on the second page. Here we had just bromine just sitting here by itself. But now we're adding some water along with it. So now instead of attaching two bromines, we're attaching a bromine and a hydroxyl group because our water molecule is basically going to screw our reaction over. Bromine is going to attach initially to get that nice intermediate, but then water is going to attach afterward instead of the second bromine. So you end up attaching a bromine and a hydroxyl group. So that's what the big difference is here. So if you see bromine and water being thrown in together, then you have to know that you're getting a bromine from the Br2 and you're getting a hydroxyl from the water molecule. And quick bonus question here. Are they going to be trans or cis with respect to each other? You got a 50-50 shot here. Hey.
Which ones are you talking about?
So the mechanism of attack is the exact same as the just Br2 by itself. So what do you guys think?
Trans.
They're going to be trans, right. So these guys are going to be trans just like the two BRs were. So when we draw them, again, we can just draw them. Here we go. We have a hydroxyl. We can have our bromine sitting down here. We can also draw it inverted as well. We have a tiny box here, so we can only draw one of them. And let's see, we have two nice chunky ethyls right here that are both pointing in the opposite direction of each other. One's kind of pointing up over here, one's pointing down over here. So we draw one of them as wedged and one of them as dashed. So I can kind of just draw them kind of something like this. because again, this wedge goes out to a carbon that then attaches to another carbon. A common mistake I see made on midterms and finals is they just simply try to redraw the ethyl group sitting out there. But what's wrong with that structure? What have I technically drawn there?
Propyl.
I've drawn a propyl at that point, right? I've added an extra carbon in here. So when you're drawing the dashes and wedges, just know that those also are going to represent carbons. So when we draw the ethyl group, this is a 1-2 carbon chain, and adding that extra branch takes it out to a propyl, which is not what we have. So does that make sense though? Nothing too terribly bad, right?
Do we have to like show how the bromine and OH attach?
Ah, good question, good question. So do we have to show how the hydroxyl and bromine attach there? And the answer for this one is no. You guys don't really need to show how these guys attach. You just have to know that they're going to attach in the trans configuration with respect to each other. Any other questions on that guy? Anything else confusing? Mm-hmm.
So there's no other ethyl group on that side?
Ah, good point there. So if we go out to this carbon out over here, the only thing we have are a pair of hydrogens. So we don't technically draw those, but if we were to draw them there, they would be dashed and wedged also. But there's only ethyls on one side of the carbon-carbon double bond. So we draw both ethyls on that one carbon over here and draw the hydrogens over here if we so chose to. But again, we're organic chemists, so we don't necessarily draw the 2 protons there. Good questions all around. Any other issues with this guy? Any other questions? Concerns? All right, what's this? What are we getting out of this guy? Yeah, H minus, minus H2 gas. Yep, those are the 2 beautiful answers I've been waiting for. We're losing H2 gas here. And where is that second hydrogen coming from? It's from the hydroxyl, right. So if we lose the H2 gas, this guy becomes O minus. So what are we making here?
No, carbonyl.
What are we making, right? We got an O minus, we got a leaving group. What are we making?
Epoxide.
Epoxide, right. We're promoting an intermolecular substitution. We're getting this oxygen to attack that particular carbon when it is negatively charged. And yeah, we have no reason to change these guys, so we can just redraw them in the exact same configuration that we left them in. Makes sense, right? Like I said, we lose this, and then our oxygen comes along and kicks bromine right out. Very common mechanism used to turn alkenes into epoxides. Assuming you don't have some, MCPBA kind of laying around in your drawer, you can just unleash some bromine and water and then throw some sodium hydride in there. Any questions on that second part of that reaction there?
Will it be counted wrong if you don't draw the wedge to dash?
Ah, so if you didn't draw the dashes or wedges here, would that be counted as wrong? So in this structure, this carbon has become a stereocenter at that point. When we turn it into an epoxide, it is still a stereocenter. So you would get docked if you did not draw dashes and wedges there. You have to indicate this guy is a stereocenter. So you have to make sure that you keep your dashes and wedges in line. Now, if we're being really, really technical, technically that carbon isn't a stereocenter because these 2 groups are identical. They're both ethyl groups. However, when we knock this bond over, or when we basically attach an additional functional group here, we want to indicate that these guys originally were on opposite planes of orientation before that attack occurred. So we use dashes and wedges for that reason. Not necessarily for the stereocenter purpose. But we would need to use dashes and wedges there to indicate that before we started any of this, the ethyls were in opposite orientations with respect to each other. Good question though. So, when in doubt, dashes and wedges away. Good questions all around though. Any other questions on this guy? All right. Oh, goodness gracious. What in the world? What have you unleashed upon us now? Okay, So let's take some general observations about this. We got an ugly chair, and all right, we got this, and we got a solvent. All right, what other observations can we make though? How can we make this a lot easier to solve? There's a leaving group down there, and what else we got? What the heck is this? This bulky base. Yes, that is bulky base. That's about as bulky as they come. And what else can you observe about it? What else is special?
A product.
Now, down here at the bottom of the arrow, we've got ourselves an A product solvent there. And there's one more observation about this guy we can make. What else?
Strong base.
He's a strong base, right. So he's bulky and he's strong. So what kind of mechanism are we doing here? E2. Bingo! See, you guys got this. This one just looks ugly because you have a chair involved. But again, we don't have to really deal too much with the chair. I'm just going to draw it as a standard bond line. All right, so this is a cyclohexane. So I'm just going to draw out my cyclohexane over here. Right? Now, if I assume that this bromine over here is sitting in our 1 carbon, I'll say this guy's 1, and this is 2, 3, 4, 5, 6, all the way around. So bromine's going to leave from our 1 carbon, and our nice base here is going to come and collect a proton. Now, before I even draw anything else, how many products are we getting from this? We're
1.
only getting 1. And how do we know this?
There's only one adjacent
There's
hydrogen.
only 1 anti-paraplanar proton to collect from. Next door, do we have any protons over here? No, methyls are in our way. We cannot collect a proton there because there's no proton to collect. So we're only going to get 1 product from this. We take this proton, and our double bond's going to be dropped right here between 1 and 6. So here's 1, 2, 3, 4, 5, 6. So I'm going to erase these because they're now in my way. But between 1 and 6 is where we're going to be able to drop our double bond. Now, does that make sense, how we get the 1 product? A lot of you guys are going to be tempted out of force of habit to draw 2. But remember, ask yourselves, can we actually get 2 products from this? Remember, anti-paraplanar, remember, the word of power that you can use to win over the love of your life. If you don't use it, then you're not going to win the game of life. You need it. So you need an anti-paraplanar proton. You see, this is forever alone territory. There is no anti-paraplanar proton over here. So we cannot get a second product. And now, as far as drawing everything else, we just have to go based on what orientation they're in the chair conformation. All right. So we got an equatorial and axial methyl. Okay, glorious. So that'd be over to the 2 carbons. So over here, we would have a wedge and a dashed methyl. We know that that's not a stereocenter, but again, based on the chair conformation, one's up and one's pointing down. And if we continue on, so 2, 3 at the 4 carbon, we have the nice methyl ethyl or isopropyl. What orientation will he be in the chair conformation? He's just going to be dashed. He's pointing down. And what else we got here? We also have over here at the... Yeah, we got ourselves right here, what, number carbon 6. We have a methyl group, but do we need to draw a dash or wedge for him? No, we don't. He's the only substituent sitting there. And that's it. Any questions on this guy? Not too bad, right? Nothing too terribly special here. All right. Now for the, oh boy, let's take a look at this guy. Actually, well, it's technically 9:08. This session was supposed to end basically almost 10 minutes ago. So I'm gonna leave this up to you guys. Do you guys want to continue a little bit further, or do you guys want to call it good here? I'll go with hand raising. I'll go with the democracy here. So, all in favor of ending the session here, raise your hand. All right, so I got a pretty decent chunk, and then all in favor of me continuing the session. It looks like all in favor of ending it's going to win out by just a little bit. So, alrighty, we will call our session good here.